but it sounds really clear on my end now. So we're going to get going. Thomas, you still there?
Yes, I'm here.
Okay, so today we've got a good presentation. It's on thermostatic radiator valves, and I've got a colleague and a friend of mine, a fun and funny guy from Germany. He knows everybody in Europe in the hydronic industry, and he's a really interesting guy, so if you get to meet him sometime, he's a good friend. But Thomas Heising is, well, I'm going to let you talk. He's our OEM in Europe, and tell us what you've been doing, Tom, and what you bring to the table here today.
Hello to everybody. My name is Thomas Heising, as Hot Rod already said. It's an honor for me to support my colleagues in the US today presenting thermostatic radiator valves. The reason why they asked me probably is because I have a long experience in selling and promoting thermostatic radiator valves, working for first the biggest German maker of TRVs and for more than 10 years now for Caleffi. So I have a rather, let's say, experienced background in thermostatic radiator valves. I'm by origin, I'm a plumber. Before I stopped working and going into sales, and I hope we will answer all your open questions, or the presentation will be that good that there are no questions left over at the end.
Well, thanks, Thomas. That was a good intro. And yeah, Thomas started in the trades as a plumber, like a lot of us that are tuned in today. I see Nathan, my friend up in Alaska, is tuned in. I know him and his dad are plumbers up there. So I think a lot of us started in this industry as the hands-on guys. And that's what I like about Thomas, is he brings some good hands-on experience as well as his knowledge from being on the sales side. So let's get rolling here. What I've got today is some slides. I didn't put as many slides in today because I want to do more talking. I want to leave plenty of time for questions. And what I'm going to try and do is monitor the questions this time as I'm going. Because what can happen sometimes is I'll get to the end and all these questions we saved to the end, and I don't know what slide they were referring to. They say, well, on that one slide, can you tell me more about this or that? And so I'm going to try and watch them as we're going. So this is where we'll start. This is basically, let's call that a cast iron radiator, something with a thermostatic radiator valve on the top. And what can you tell us about the pictures here, Tom? I mean, that seems to be the preferred way. If you can, put the valve on top, and it shows kind of what, I mean, valve is just really a switch or just like an on-off valve, right?
Let me start with some basics about thermostatic radiator valves. First question is, why should I use thermostatic radiator valves instead of manual valves? Most of the people know, but the TRV, I would like to say TRV, it's shorter than thermostatic radiator valves. The TRV is a self-acting proportional controller working without additional energy, and that makes it so interesting because this is a valve which saves energy. And while saving energy, you save money, because saving energy means saving money. And this is one of the a few products in the world which pay themselves back by saving money. On the other hand, by saving energy, you save the environment, you use less energy, and you have a fantastic, comfortable room temperature control by this. This is probably the cheapest possible room temperature controller you can use with radiators, and the amortization time of it is rather short. It's important that you keep a constant controlled room temperature. And to understand the energy saving potential of this kind of valves is that you can save around 6 to 7% of energy by reducing the room temperature by only 1 degree. So it is built for compensating external energy coming into a room. Might be people, might be the sun shining in through the window, might be electrical appliances in the room. All this manual radiator cannot compensate. A TRV is doing that and closing if an external heat source is bringing heat in the room. And that's why this valve is so energy saving and cost saving.
I really like the way you put that, because that's something you don't think about when you put in a zone valve that's electrically powered, that's got a either a heat motor type or a motorized type of zone valve. I mean, it uses, for the life of that valve, it uses electricity. It's got moving parts in there that are potentially can break down someday, an end switch in the motor, something like that. But with this valve being so simple, it gives you like almost a reset control. It compensates for, like, say, when you get a high room load, a lot of people come into a room and all that energy from the people in the room, it can compensate for that. And it does it proportionally. So it gives you all those things in one simple package. It's really, I think it's been overlooked a lot for what it can do, for what it costs, and how long it's going to last. So that's a great way of putting it. Thanks, Thomas.
installing the valve in the right way that it can sensor and measure the room temperature in the best way. You have, for example, a control difference of below 0.5 Kelvin in the room temperature, far below, and you have a perfect and constant room temperature control. It's really comfortable to use this, beside the big aspect of energy saving.
Yeah. Now Nathan just asked a question. He said, "Does it have to have a constant fluid temperature coming to it?"
No. It compensates. The steering value is the room temperature. It doesn't matter the water temperature coming in. It has a small influence only, but this is measured by the standards and can be neglected more or less.
Yeah, so it's just watching. As long as there's enough heat coming through, enough energy coming through the pipe, the valve is just going to respond, and it's responding to the air temperature basically.
Yeah. Thermostatic valves are mainly made out of composite to prevent air transferring from the valve body to the sensor, which is built in the head.
Oh, that's a good point. So people say, well, it's plastic to save some cost, but really it's
no. It's to prevent.
For a reason.
Yeah.
Okay, that's good to know. All right, then in this picture, what we can see here at the top, and the picture kind of tells the story here, is the color of the radiator at the top is blue, means it's cold, and then at the bottom, as the valve lifts off its seat, the warm water starts coming through, and there we're showing it coming in the top and then returning out the bottom. And I think we talked about this little, we practiced, Thomas and I, on Monday, and you said ideally you'd want that valve up high like that instead on the bottom, just so it can sense the room temperature at a better level in the room as opposed to being right down at the floor level, correct?
Yeah. Right. The valve. Please never install the valve as you see it on the picture, not vertical mounted, always horizontal mounted. This is just to have the cut to see how the spindle closes the seat. Yeah. But the installation of the valve is not optimal. It should be horizontal. We should look on the head.
Oh, so when you stare at it,
just to demonstrate the function.
Yeah, I see. Yeah, so this is in these pictures we got it shown it vertically like that, just so you can show how the valve comes off the seat and stuff like that. But ideally, you'd want that valve facing out at you instead of up horizontally, is what you're saying.
A valve in this position would, for example, influenced by the valve body, so the hot air would go around the valve body, would go in the head. The head would have simulated a higher room temperature than it in reality would be, and it would close earlier.
Ah, so it's getting full just from the heat coming off the body of the valve going up, rising up.
The heat gets stuck in the head. The sensor thinks, okay, warm, I close, even if the room temperature is not reached. So vertical mounted, they don't work properly. This is just to demonstrate, to see the seat.
That's a good point. Thanks for catching that. Yeah, that makes sense that it's being fooled a little bit by the body temperature coming up. I'm trying to read some questions as we go here, but I want to keep moving because I know we've got some slides to get through. So these are some different applications here. I think Thomas can talk about this. We're trying to show all the different applications that you could use a thermostatic valve for, not just on the heat emitters here, where we're showing some panel radiators, maybe a towel bar, some old cast iron radiators up at the upper center portion of the screen up here. Call those cast iron radiators. That would be a towel bar in the bathroom or something like that, some panel radiators. But also it could be used down here as an injection temperature control for like injection mixing to this, taking the high temperature off this primary loop here and allowing just the right temperature to be injected into the radiant to get a mixed down temperature for these lower temperature zones too. And it's used in conjunction. So there we've got it mixing down a temperature going out to these lower temperature emitters, and every one of these has its own, and that's what Thomas was saying. You can see how the valves in these pictures are all shown off to the side instead of standing up vertically.
Yeah. The injection valve is available in two temperature ranges, one to control, for example, hot water storages, and another one to control underfloor heating systems. Mm-hmm. The range, I have the range only in mind in Celsius, between 20 and 50. I don't know what it is in Fahrenheit, and the other one between 40 and 70 for hot water storages.
All right. Anything else in this picture? I think that's pretty. Basically, what we're showing here, we're going to talk about both different applications. And this is what we like to call home run piping, where every radiator in this drawing here is getting its own supply and return, as opposed to the where they're in series, where you feed one to the next, like we would typically do a baseboard, fin tube system over here. So this is a nice piping method also.
Both systems are classical two-pipe systems.
Mm-hmm.
which are recommendable.
Yep. So we'll call that a two-pipe system. Okay. Let me move to the next slide here and keep going. Oh, he had some things kind of rolling in here. So that's just kind of what we talked about, the different types of connections and things. We'll get through those as we go through. We're going to show some slides that will show the different valves and different temperatures. So there's a cutaway of a radiator, and this really hits home on how the valve controls it and how the fluid goes through a radiator. It comes in the top there, and it goes down through the, that's a nice drawing. It shows how the fluid moves through a radiator and how the convection currents come up to draw the heat off of that radiator.
Yeah, this is a special radiator with integrated valve. The valve body is welded in. It's made out of steel and welded in the radiator. Right. And the cartridge, the thermostatic cartridge, is then sitting in this steel valve body. The seat of the valve is made of steel. You see there, right? And outside, where you see now the red protection cap, you install then in case thermostatic head. So
this could be taken off, and then the head would go on. This is a common thread right here.
Yeah. Yep. Our heads are made for cartridges with a thread M30 by 1.5.
Which seems to be a fairly common industry.
Yeah, it became a kind of standard, this connection.
So if you get a radio that has that mechanism already in it, it's a good chance that our operators will fit on that, the TRVs will fit on that thread.
Other radiators without this thread, you don't find a lot. The makers might offer adapters.
Oh, okay.
For heads M32 by 1.5.
I see. Yeah. Okay. We talked about this a little earlier. Here's a typical home run system using PEX tubing running out to the different radiators in different rooms, and every one, of course, would have its own thermostatic valve on it. So every radiator, not only every room in this drawing here in this building here would have temperature control, but every radiator would also. So if there's multiple radiators in one, maybe one's over by the bedroom and you want to have, or by the bed and you want to have that a little bit warmer than you do the inside of the room, you'd have the adjustability on every one of them. And there's a kind of a schematic of what a home run piping schematic would look like there. And you can see the TRVs mounted properly there. And a good thing to notice here too, Thomas, is that the size of the piping going out to these can be fairly small. I noticed when I was over in Germany, I would look around when I was visiting different businesses over there, and especially around Heidelberg, because a lot of the older buildings had been retrofit with panel radiators, and they would have like a 15 millimeter, I guess is what you call your copper tubing over there, 11 millimeter.
50 millimeter is a kind of standard connection. In some other countries, like France or in Scandinavia, you find even 10 millimeter tubes, 12 millimeter, very thin tubes.
Yeah. And that's a nice way
but in old building and retrofit, it can go up to 1 inch, 1.25 inch. Old gravity systems being converted.
Okay. We had a couple questions about remote sensor bulbs. We'll get to that in a second. All right. Anything else on this? I think that just shows how you can combine the thermostatic radiator valves with a home run system using our manifolds also.
Yeah. I would like to say that, for example, TRVs in Germany are obligatory. They have to be installed since the mid of the 70s. After the first oil crisis, we got special laws in Germany that TRV, room temperature control, has to be installed, and the TRV is the easiest way to fulfill these standards. And more countries followed later. That more or less all over Europe, the thermostatic radiator valves are standard.
Hey, here's a good question. I try to monitor questions as we go because they pertain to the slides. John Siegenthaler's tuned in today, and he said, now, if you're using this head with a remote sensing bulb on it, then it wouldn't be so susceptible to having a vertical mount, right? Because the sensing bulb is really doing the driving, right? If you had the sensor mounted remotely.
Yes.
So that would be one application where you might be tempted to put the TRV vertically, but you've got your sensing bulb.
Yes,
I'm going to show that as we go here.
It will come on one of the later slides. If you have to, due to space reasons, if you have to install the head vertical, use a remote sensor for sure.
Okay.
But we'll talk about later when we see the remote sensor.
Yeah, exactly. Okay. All right. I think that's good on that one. That happens to be one of the installations up at our office in Milwaukee, at the Caleffi headquarters up in Milwaukee. I think that's just a DIA norm. With the, you can see what they've done there is this, the tubing for this job came out of the slab PEX tubing came out of the slab when they poured the slab, so we put this little box so when they're cleaning in there, they're not ramming into it with the Hoover and stuff. So that was a site-built piece there.
Yeah.
I think that just shows our typical number right there with the temperature range that you were talking about, the 45 F to 82 F.
85, that's a normal room temperature controller.
Yeah.
The range for room temperature.
Mark, this is Mark's office up in Milwaukee, our CEO up there, and he's so proud of these valves. He's even got a picture of them there. He's got them in his room, and he's got pictures of them too. He doesn't want to forget them. And there shows some of the fittings that are available. On the bottom left there, did that just pop up on your screen, Thomas?
Yeah, these H fittings, because in the radiator, the welded-in valve is only the supply valve. So, but you have to install a lock shield normally, but instead of lock shield, you use these, we call them in Europe H fittings, where you can shut off the radiator and take it away for renovation or whatever. They have, you see here on the picture the angled version where the tubes will go into the wall or coming out of the wall, and there's a straight version where the tubes go down in the floor, which you see on the picture of the radiator. They have covered it with a white cover.
Yeah. Okay. And there's the thread that we keep talking about.
Yeah, that's M30 by 1.5, where our head fits on. This is a special cartridge where you see figures on. So it's a presettable cartridge where you can preset the volume. So you give the room only the volume it needs to fulfill the heat demand. It's a little balancing.
Yeah, a little spanner wrench goes in. So yeah, basically.
Yeah. I'm sure this maker has a special key for it. Mm-hmm. It should be supplied then with a radiator.
And this is typically what you'd see when you bought this radiator. It would come with that in there, perhaps, right?
Yeah, it comes with it in.
Yep.
Because it's pressure. It's a leakage tested in the factory, so it comes in. Normally, there's now a plastic cap on just to protect the thread.
Now, if you had this, when would you set the flow on this? Because that's basically what this little flow meter is doing. If you had multiple panel radiators in one room and you knew what the heat output of each one had to be, you could correspond that to the number on there. Is that what they're intending you to do with the balancing valve?
Well, it's to balance all the radiators among each other, because water has a tendency to run through the first radiator, preferably, and maybe the last is not supplied anymore with enough water. So you can throttle the first radiators and then keep the last radiators open to have the water balance in the system.
Yep. Yeah, that makes sense. And you've got some little tricks for attaching it, a simple way to attach the actuator.
Yes.
When you put it on.
While installing the head on the radiator, please open it fully on position number 5, because it's much more easier to install then.
So you don't have that spring tension working against you as you're trying to get your
Right. Mm-hmm. Especially when it's very warm inside, the sensor closes, and you have to push the spindle of the cartridge in. So always put it on 5. It's much more easier to install, and then go back to 3, which should be okay, which is a normal room temperature.
Mm-hmm. And that would correspond, what did we say, to about 70 degrees, 68 or 70 degrees number 3?
It's 20 degrees Celsius.
Okay.
I don't know how many Fahrenheit that are. And each figure in between are 4 degrees Celsius difference.
Okay. Yeah, we can do the conversion on that. All right, now there's probably the nuts and bolts of it. This is probably where you can spend a lot of time talking about what's different about the Caleffi and what's so unique about the Caleffi.
Yeah. It's a nice picture, because we can explain several things. For example, the element you see on the top, which, this is the heart or the brain of the head. It's filled in, we have a liquid-filled sensor. There are 3 known sensors on the market. It's the liquid-filled one, it's a gas-filled one, and it's a wax-filled one. but the others, I mean gas and wax, we find not interesting, because the liquid-filled sensor has the best performance. Gas has a problem that it's rather weak, it's compressible. So you have to design the spring, the return spring in the cartridge, rather soft, not down the spring in the body, rather soft. Yeah. Wax wears out. Wax-filled sensors wear out after years. And the big advantage of liquid-filled sensors is it's a very strong one. It has an extremely long lifetime. And it became, in the meantime, standard because most of the heads you will find on the market will have liquid-filled sensors. Please pay attention that you buy a head with a liquid-filled sensor. It's an enormous advantage. Yes.
Yeah. You just get more strength out of a hydraulic than you would, let's call the air-filled is almost like a pneumatic operator as opposed to hydraulic with the liquid in it, so you get a better controllability. And then, like I think you said, you can put a stiffer spring in here when you have a hydraulic one, which means now you can get better shut-off. I'll let you talk about that.
And here you see that all the components in the head are made of composite. It is to prevent the sensor to take contact warmth from the body.
So
even the stainless steel stem of the body has no direct contact with the sensor because there's a plastic stem, the composite stem in between there, the black one.
Yep.
It is to prevent contact warmth, contact heat going into the sensor. That's very important.
Oh, that's interesting. So the fluid coming through here would warm the stainless steel shaft at the bottom here.
Yes.
If I put a composite piece in here, you break that. That's like a thermal break in there, so you don't get that temperature up into the.
Yeah.
All right.
To the valve body, you see that we have a double O-ring sealing around the spindle, which is important. It's a double O-ring sealing, which is safe. You there one and there, so leakages are more or less unknown around the spindle, which is very important. And you see on the nut and nipple something which is unique. We have on the conus an additional O-ring to seal on the union on the nipple of the valve, and we have at the thread of the valve an EPDM sealing. You don't have to use any additional Teflon tape or to screw it into a radiator.
So this, you got the nose seal here with the O-ring here.
That is an O-ring which supports the conic sealing, and there is on the thread is another sealing.
So you got the sealing here, you got the brass touching the end, and you got the O-ring on the nose of it also.
Yeah. So no leakages should occur.
Yep. Okay. I think we got some better shots coming up of how the indicator for the setting that you can lock and put the lock shield and stuff on it.
Yeah.
So
the liquid is okay. It's a chemical liquid. Easily spoken, it's a kind of alcohol which expands. The expansion is around, which results on the disc, is around 0.22 millimeters per Kelvin temperature change, and the full stroke of a radiator valve is around 2.53 millimeters, not more. So it's a rather precise instrument, let's say, control instrument.
Yeah. Okay, that's good. A couple questions were on the slide. Somebody asked Frank, a friend of mine back in Philly, Frank from Philly. Hi, Frank. Hey, no, we don't make radiators. Caleffi doesn't make radiators. We just make.
No, we don't make radiators.
Yeah, we're basically a brass company, and we make control parts and all the different things to put things together. But we don't make boilers or radiators or pumps. We're just kind of the accessory guys.
We focus on valves.
Yep. Okay. Let me see if there's any other questions I can get to while we're doing that. Is there a notch in the adjuster to have a starting point? So I'm trying to think what you would mean there on the. I don't know if you mean on the adjustability or when you put the actuator on the top here.
Yeah.
But
even if you put the actuator on the top, it has already its control position because it has taken the temperature of the room before you install it.
Oh.
There's no starting point, because as soon as we assemble everything here, this valve starts working, even during transport, in the ship, on the plane, because it's a proportional, continuous controller, proportional controller. It always works with a temperature difference.
Yeah, wherever it is, like you say, whether it's in the truck, get shipped to the job, or at the job site, it's always proportioning its thing. They're not repairable. Somebody asked, is this a repairable device here, this head? I think you would just repair
No, because each head is adjusted in the factory on the assembly line. So you cannot change parts All parts belong together in one head.
Okay, so they're calibrated.
It is calibrated. It's adjusted to give you the room temperature of 20 degrees at position number 3.
Okay.
At an opening of the valve body of 0.44 millimeter.
Okay. I think what Bob was asking, he said that he meant that CV adjuster shown in an earlier slide. Where is that set? But that would come from the radiator manufacturer. That's not a component we make.
Yes, the one we have seen, which is built in the radiator, comes from the radiator manufacturer.
Yeah. What another question?
We have valve bodies with integrated presetting, where you can do it with a valve body, if you don't have a radiator with built-in valves.
Yeah. And this thread, this same thread is what's on our manifold and also on our zone valves.
Yes, yes, so it's M30 by 1.5.
Yeah, so that operator could be put on a zone valve. If you had a zone valve, for instance, in a baseboard enclosure, and you wanted to turn it into a thermostatic operator instead of off an electric or wall thermostat somewhere, this valve could be put on that. The other question is, do different valves fit on different manufacturers? For the most part, I think you said there, I think we'll get to that a little later on, you said the standard was established in Europe, and pretty much everybody manufactures that standard as far as the thread and the pin stroke and all that, right?
Yeah, yeah. So it's not a written standard. It's not written down somewhere. It just became a kind of standard to use the thread M30 by 1.5.
Yeah. Okay. I'm going to keep moving on here. I know I got I'm trying to do a lot of questions, so I'm going to have to get to some of them at the end. And this is, I think, what you're talking about, the listing. There is a listing and a rating on them, as you can see here. It's kind of like there is on circulating pumps, where they have the color bar there on the left.
Yeah. This has now, or last year, been implemented for Thermostatic Radiator 2. It's a thermostatic efficiency label. You reach it if you fulfill several criteria. And we got for our head this year the efficiency label number A, which is the best one.
Okay.
You see the criteria down there. It's the influence of water temperature to the head. It's the hysteresis of the head. It's the response time to changes in temperature, and the influence of differential pressure. And if all these values are good, you get this fantastic label.
So they developed a standard that if your valve meets all their numbers on this, you get the different.
Yes. They take the values out of the European standard. We have a European standard for our thermostatic radiator valves, and they are all controlled, measured in labs before they get the approval by the standard. And these values are valid to calculate if you reach an A, B, C, or D.
Great. Okay. Well, that's good to know that we're the best color on the bar there. Question now, the disc can't be replaced at the bottom. Also, that came in when we're back on the previous slide. You wouldn't take that out.
In the valve body, the disc.
Yeah.
Can theoretically be changed.
Go back to that. This right here.
Yeah. But theoretically it can be. But you have to drain the system. You have to take off the cartridge. You have to change the disc. It's probably better than to change the complete valve.
Yeah. Well, because if that gets compressed or something, there gets a mark in it, I guess I don't know why you would want to change that. I don't know what would ruin a disc in there unless like there's a lump of solder or something got stuck in there and made a mark in it. But not a very doable thing is what you're saying. I don't need that we even offer the disc separately.
No, we even don't offer spare parts.
Now, there was a question came earlier. I was watching if we offered it with this thing, and we're going to get to that in a second. So that's a picture of the remote sensing valve.
Remote sensor, yeah.
Yeah. Okay, the locking device.
Yeah. We have at the bottom of the valve, there's a wide ring in composite you can use for several functions. You can limit the temperature. That means if you adjust it in the right way, you can close the valve and open it just to a certain position. You limit the temperature. Or you can lock the temperature, fixed on position number 3, which would be 20 degrees room temperature. That is possible. Each head has an integrated frost protection, which prevents that the radiator or the tubing freeze in winter. So this valve opens, this head opens at about in this case 45 Fahrenheit, to prevent that the tubes or the radiators freeze in. It's a built-in frost protection.
So if a building was left empty or something in the wintertime, the owner of the building could just go around and set them all in the freeze protection, so it would use the least amount of energy but keep the building from freezing up.
Right.
Okay. All right, I think that's pretty good.
It's a small snowflake as a symbol on that.
Yeah, I saw that. So that's the freeze point. I think we see that on other things. That snowflake on European controls.
Yeah.
A sunshine and a snowflake, I think, are the two things that I like to use over there. All right, we talked about that earlier, but here's
So we have different kind of valve bodies. We have angled, we have straight, and we have axial, or you see on the right side. So you always should be able to find a valve body to have the head horizontally mounted. Mm-hmm. That's important, because only horizontally mounted, it can feel the room temperature the right way. You see very well on the very right picture where the actual valve is. You can see that the sensor is really in the room temperature on top.
Yep. Yeah, it's all the way out as far as the radiators it can get.
This is a perfect application, for example.
Okay.
And below you see, don't put a built-in sensor, a head with a built-in sensor behind the curtain or behind the cover, or where it's influenced by the sun. Yeah. If you find these applications, please use a remote sensor or a remote dial instead. Okay, because in all these cases, the temperature sensor will be influenced.
Yeah, that's a good point under the window, which would be a fairly typical place to put a radiator to overcome that heat loss right there. But if the sun comes in and can see that radiator head, then you're going to have a
But normally the sun does not shine directly on the head.
Yeah, well, with the window
rare.
That would be But it's something to know.
Below the window is a good position for a radiator, because the convection is best below the window,
where the cold temperature's coming down from the window and the heat to the radiator.
Yeah.
All right, this we put in. I'm not sure who sent us this slide, but thanks if you're up there and you see this and you recognize it. But here's somebody that put it looks like a little electric boiler in and then ran the hydronic system to heat the shop. And I don't know, another option would have been some electric baseboard, but I guess he liked hydronic heat enough that he put electric boiler in and piped it just a few feet there to these two nice panel radiators. Just a nice looking installation. But there's an example of, radiators under a window where I don't see how the sun could ever get in and get to one of those valves.
Oh, it's a perfect use.
Yeah.
Looks good.
Yeah. All right. Now this is the big thing about the two different ways to pipe them, is a one pipe system or two pipe, because we make both valves. You got to know which valve you're applying and why. So I'm going to let you, Thomas, tell us what's.
Yeah. We have the H fitting below in two versions. One is for two pipe systems, which I personally recommend and prefer, and we have one for one pipe systems. The one pipe system H fitting has an integrated bypass where you see the water going through to the next radiator. And
so even if this radiator valve would shut off on this one, the next one.
Yes. If the valve is shut off, there's always a flow through the bypass to the next radiator.
Yep.
Yeah. It's a typical one or single pipe system.
Now, Thomas, this is a classic example, of where you would set the flow rate like we showed earlier on that little CV setting on those, where when you got three of them in series here, you might want to flow this one down to make sure you get enough flow down to the end one, right? Is that where that valve would possibly be used?
Yeah, but you have to be very careful in single pipe systems with throttling, because it lives from low resistance. One pipe systems is. So you should have as less as possible pressure losses in. So in the one pipe system, I would leave the cartridge fully open.
Okay. Oh, I just got I'm kind of reading as we go here that Paul Roars from Lochinvar said that was a job that he did for his brother-in-law's wood shop. Well, thanks for sending that, and I'll make sure I get a credit on that slide. All right, sorry to interrupt there. And then the two-pipe system, again, the preferred method, this is what we showed with it. Could be a home run system, but it is a different valve that goes in here, and you need to know that this valve up here wouldn't be used for a two-pipe system. We're going to have some close-up pictures of that coming up, but this is a good graphic of explaining that.
Yeah, they're easy to detect because one has a bypass, the other one not.
Yeah. Okay, anything else on here? You think we got that one covered? I'm looking to see how many slides we got to get to here. We better keep moving.
This picture doesn't show the reality, because in a one-pipe system, the following radiators have to become bigger and bigger to the end, because you lose supply temperature.
So really,
the first one is the same as in a two pipe. The second one should, in a one pipe system, already be a little bit bigger because the supply temperature is reduced because it's used in the first radiator. And then the third one should be even more bigger. That's one of the disadvantages of a one pipe system, that you need bigger radiators until you reach the end of the circuit.
Well, and also what we should do is change the color of these pipes so they get a little bit
lighter.
Yeah,
right. It should get start with dark red and becoming lighter and lighter.
We'll work on that. Hi, gentlemen. On the one pipe system, how much pressure drops through the H valve?
Well, we have a chart in the literature to see the pressure drop.
Of course, it depends on the flow rate, right?
Yes.
So that would be in our information that we have online.
Yeah. We can adjust the bypass a little bit between 35 and 50%, so we can play with the opening of the bypass.
Yeah, and I think we're coming up on a slide that should explain that a little better. Okay, then the next question: the two-pipe system, a differential bypass valve is also required?
It depends on the system. If it's a well-balanced system, you should not be forced to use a DP controller. And it depends on the size of the system. If you have a big building, it's always better to use DP controllers or any kind of balancing valves.
Like a big commercial.
But different pressure is not a problem as long as the pressure does not exceed, Bob, you have to help me now, not exceed 0.2 bars. I don't know how many PSIs that are.
Yeah, bar's about 15 pounds, so
0.2 bars should not be exceeded. Then you have no noise problems in the radiator valves.
You won't have a high velocity or an issue.
Yeah.
Noise issues. Okay. What about the new Delta P pumps? I mean, I think that's another good application for this.
Yeah, that's a very good application. And in the past, in Europe, we all installed different pressure valves between supply and return, which opened then automatically at 0.2 bar to reduce the pressure. But now with the new high efficiency and DP controlled pumps, this becomes obsolete because the pumps control themselves. If the pressure increases, they slow down themselves.
Yeah.
That is a fantastic issue, these kind of new pumps.
Yeah, I think Frank had a good observation on this one up here. He said that basically comes like what we call a monoflow T here, where you've got this line going and it just allows a little bit of the energy to go up to each one of these valves here.
Yes,
so
yes.
That's a good analogy.
Yeah. So if the radiator is closed, 100% of the flow goes through the bypass.
Mm-hmm.
And if the valve is open, a part of the flow, which is adjustable, goes up through the radiator.
Yeah, and I think we're coming up on that slide now that shows me.
Yeah.
But so here's the different variations, and you can see. I'll let you explain. Starting from the left, you can see why there's a difference in those valves.
Yeah. On the two-pipe version on the right side, you see the connector in between is just a space holder, not more. On the one-pipe system, you see there's a real bypass between supply and return, and behind the small brass cap there is a screw where you can adjust the bypass.
So you can take that chrome cap off, and there's a adjustability in there.
Yeah, and look on the diagrams, and then you can adjust the bypass.
It'll tell you what the number corresponds to, or something.
Right, with the turns, right.
Yep. And then these are shut-off valves, isolation valves if the radiator.
Yes, there's more ball valves in.
Yep. So if they want to service it or paint behind the wall or something, that's what that's for.
Right.
And then we talked about the adapters here. Sometimes those will be in the radiators.
Yes, we have two kind of radiators. We find one, or mostly today, with half-inch female threads, where these kind of adapters can be used. Mm-hmm. But some of the radiators have 3/4-inch male threads with conus, where you use just a brass conus in between.
Okay.
It depends on the radiator maker.
Yeah, and I think we got some.
You might find both on the market, and we have both adapters, this one and the brass conus.
Yeah. And the other nice thing about our valves is that all the fittings that work on our radiant manifolds also work on them. So if you want to use, over here we show PEX-L PEX. We've got a really nice fitting for the PEX-L PEX with the double O-ring in it with the good gripper ring. We've got the one with the segmented olive here for regular type of PEX. It's got a nice nose seal on it here, as well as the O-rings in here. They've got isolation gaskets up in here, so the aluminum wrap and the PEX doesn't touch the brass. And then we've got the sweat over here, and the compression.
It should be suitable for all applications.
Yep. All right, this shows a little bit better what our PEX fitting. What's nice about our PEX fitting is we've got that nice Venturi going through it. We bore it out with a little bit of taper, so we get a little better flow than just a straight hole going through it. I guess that's the intent behind that, Thomas.
Sorry?
The
yeah. Okay. This is yeah.
On that PEX.
The PEX fitting, yes, it's a perfect fitting. You see, with the double O-ring sealing, if it's installed right, it will never start leaking again.
Okay, we're going to remember you said that.
Yeah. Bob, I said if it's installed right.
Okay, yeah, that's a disclaimer. Now here's a classic example of somebody who went to a lot of trouble to build their own adapters on this radio. So you can see they got a copper to male adapter. They soldered a piece in there, then they soldered that looks like a Kitech adapter or something there to me. But I mean, there is a fitting that we make that we just showed in the previous slide that would do that all in one nice clean connection, so you don't have to have all that homemade fitting in there.
Yeah, and what is missing is a shut-off function, which is very useful.
Yeah. There's no isolation, so by doing it over here.
So if you take off the radiator now, you have to drain the whole system.
Yeah, or if you had a leak on one of these fittings or something like that, whereas over here, we give you, we give you everything in one fitting. You know, the other thing it does, it brings your connection up out of the off the floor a little better, so you can get your wrenches, and if you have to, you know, get in there to assemble that, you got a little bit more space. So.
And the distance is all the same between the extra distance in this radiator is all the same. It's all 50 millimeters.
The spacing.
You can buy any radiator with integrated valves. They have all an extra distance of 50 millimeters between supply and return. Okay.
So that's something everybody applies to that standard or agree that's the way to do it.
Yeah.
Okay. Two-pipe valves. I think we talked about this a little bit. Again, you can see there's no crossover in there. That's just a solid brass piece just to hold the spacing in the middle there, right?
Yeah, right. Yeah. Right. And this is straight version, when the tubes comes out of the floor. I recommend I recommend, for example, not to use this with PEX, because in case of somebody goes with an aspirator down, that he does not destroy something. With steel, with copper, no problem to come out of the floor. I personally would use the angled version for PEX coming out of the wall.
Yeah. We talked about that a little bit. Just to keep the PEX out of harm's way, if you have a PEX coming up out of the slab and somebody hits it with a vacuum, they get sheared off right at slab level, and then you're going to not only have a leak, but it's going to be hard to repair that. So that's why I think that picture we showed the very top end of the presentation. We had a box built around them in Milwaukee, just so the cleaning service doesn't come in and get carried away and damage the PEX tubing coming out of the slab. That would be a hard thing to repair. Again, just a close-up shot here of the one-pipe valve with the shows a little bit better of the adjustable bypass in the center.
Yeah. You can see it's adjustable between 30 and 50%. So the factory setting is 65% to the next radiator, 35% to the radiator where it's built under. But you can adjust it. The 35% you can adjust between 30 and 50%.
Yeah. Okay. We must have a TACO rep watching. They said the new TACO Bumblebee pump is perfect for the volume for this type of valve. All right, I think we've got that one good here. Let's get a handful of slides left.
Towel dryers.
Yeah, towel warmers.
Very fashionable to use in Europe, and very practical. I have one in my bathroom too, and it's nice to dry the towel with this.
And these are the different valves, the chrome-plated, nice-looking valve. Again, this
below are the lock shields or isolating valves to shut off the radiator. On top are the
TRVs.
The head, and the valves below belong to it. You install the head on the body there.
Yep. And this would be a manual valve if you just want to just open and close that manually.
Yeah,
right?
As long as the head is not on, you can use it as a manual. They're convertible.
Okay.
So you take off the manual hand wheel, and with a small adapter you can install the head then. So you can start, for example, during the building phase, during the construction phase of the building, you can start with a manual valve, and when everything is done and all people are out of the building, you can then install the actuators.
Yeah, so they don't get damaged through the construction.
Right, or not damaged or not dirty by color or whatever. So you install them at a very late moment.
And then somebody asked, there is a wrench we have available that goes in to screw these nipples in, so you don't have to put a channel locks on that goes inside.
There we have two different execution. One is with an Allen key you will have, and another one has a special key, but you will find in your toolbox a tool where you can screw it in.
Yeah. Frank just asked, is there an indicator to tell the adjustment through the bypass on the last picture? So I think
no, you have to count. You have to count the turns.
Okay, and the turn
diagram.
So the diagram that comes with it.
Yeah. You see the turns, and then you close it, and you open it, and then you see the turns. You have to count the turns.
Okay. All right. All right, pretty good. We're getting questions, and we're getting a lot of information here. Not just another.
Yeah. I don't know how many of these towel dryers are made in US and they have MPT threads, but probably the European ones coming over have metric threads.
Yeah, we talked about it. I don't know if there's any panel radiators or towel bars that are made in the U.S. You're right. It would probably have an NPT thread on it if it was made here, but typically they're going to have the
but we have, I guess we have both versions available, NPT and metric.
Okay. And there's the manual valve and shows.
Yeah. This is still the manual. You take off the manual cap and then install the thermostatic actuator later.
So really, the cap's going on that M30 thread that's under there is all it's doing.
Yes, these convertible caps need a small composite adapter. Maybe we see it on one of the pictures later.
Okay.
But it comes along with the head.
Okay. And then the other thing too, we've got the rubber seal on them where the snip goes into the radiator.
Very comfortable. You don't need any additional tape or hand to seal it. It's on. You see, it's on the nipple.
Okay. So and there's the
that's how it's converted. You see, you remove the cap, remove the knob, you install the adapter ring, which is a small gray ring, and then you screw on the actuator. Very easy. You convert a manual valve to a thermostatic one. For example, in case that somebody invest in an apartment building, having 10 apartments built and renting them out, for example, in the apartments which are not rent out so far, you just keep the manual valve on, and the very late moment you install the head.
Yep. Okay.
Yeah, there's the adapter ring again.
Okay, so just a little gray composite ring that goes to change the thread, basically, is what it's doing. It's just increasing the size of the thread like a
M30
like
by 1.5.
Okay. Cast iron radiators, and there's gazillions of them out there. That's a big market here in the U.S., Thomas, is cast iron radiators. You know, certainly in the New England market, this is very common.
Still new cast iron radiators, or are that old ones renovated because they look?
Yeah, a lot of people that do renovations like to keep the old radiators. So
they do sandblast them and then use them again as a decorative piece. What you see here on most of them is that the radiator valve is at the bottom of most of these. That should not be. You should have, if possible, a diagonal flows. Means the thermostatic radiator valve should be on the top, and the lock shield or the isoclave at the bottom.
Yeah. So these are what they're doing here is they're taking off an old manual valve and just putting the thermostatic valve in its place, but you don't have a good, like you said,
you don't have a good temperature control, and you lose performance of the radiator.
Yeah, because it's just kind of short cycling across the bottom of it.
Right. The best if it would be on top. And as they installed here, the head might end vertical, so you should use a remote sensor, or use an actual valve body to have it not vertical.
In the right configuration. Yep.
Yeah.
Okay. But we do, I guess what we're getting at here with the cast iron radiators, that we do have the valves in an NPT thread also. So obviously anything that's, those little cast iron radiators aren't going to typically have a metric thread unless it was an imported one. So we have the valve available that'll go right into that without any kind of adapter.
Yeah.
And there's the part numbers. All this stuff is online now. Also, our new price book, by the way, is online. I think I got a slide at the very end showing that. But
please go back, Bob. What you have to respect on all valve bodies is there's an arrow on the flow direction. It has to be respected.
Yep.
If somebody mixes the flow, a thermostatic head starts hammering. You will identify it immediately. This noise, it's a knocking noise. You know immediately wrong flow direction. Then you have to change the piping. So always respect the flow direction.
So it has to be in that way. It's not a bidirectional.
No, it's not bidirectional.
And there's always an arrow cast into them.
Always on. Yeah, always on. Yeah, all the different heads. The wall mount thermostat, a remote dial. What you see there is a small capillary tube, which where the radiator or the valve can be placed 2 meters far away from the remote dial. Yeah, you have the remote sensor, and this is what you have just the mouse on, is the arrow on is the immersion sensor, and this is a room temperature sensor. On the right side, the 502, this can be used as an immersion sensor, for example.
So typically you'd put that in this little well here.
You put it in this well, yeah.
Into a tier right into the fluid.
Yeah.
And this one could just go like, we talked about that, like maybe under where the convective airflow goes up through the radiator or something.
Yeah, besides the curtain, if you install it vertical, you can place it somewhere where it can measure the room temperature. The best position for this remote sensor would be in the middle of the room where your lamp is now hanging, because then it would detect the room temperature perfectly, but nobody wants to have it there.
Right. Yeah. Or where you're sitting on the couch, I suppose.
Yeah.
Maybe someday we can do that with a Wi-Fi, that you can sense the temperature from where you're moving around with you.
Yeah, probably.
Then, now, one question here. Let me get to Nathan's question. He said, the TRV on the supply and the autoflow on the return side of all the zones to dial on the exact flow? I mean, really, you don't need the autoflow on the return side, right? Just the TRV will do that?
The autoflow on the return?
Like talking about a balancing valve, like a
balancing valve. No, but I would not install a balancing valve close to the radiator. A balancing valve is something for the risers. The radiator you can balance with a presettable cartridge or with a lock shield, with a isolating valve.
Do the balancing right with the valve.
Yeah, the balancing do on the risers. It's enough.
Okay. Now, cap tube length, that's a question. What's available on this? We're going to run out of time here. I think we got 2 different versions of that. I should know this, but sorry, this is a new product.
The capillary tube is 2 meters long in all our cases. I guess on demand, if there's a building where you need longer, we can change and we can build something special. But normally they're all 2 meters long. It's 6 feet, around 6-7 feet.
How long could you go? He's saying he needs some with 30 feet. That's quite a ways.
30 feet is a lot. The longest probably might be 15 meters, which are 15 times 0.3.
Yeah, well, that's 40, 45, 50 feet probably.
Yeah.
Okay.
But be aware that it's a tube. You cannot bend it too much. Some people cut it and then take 50 centimeters out because it's too long, but then they destroy it. It's really a tube where the liquid is in.
Yeah, it's a towel. Yeah, it's got a fluid. It's a capillary tube. It's not a wire, so you can't cut.
Yeah, right. But if you cut it, you don't see the liquid coming out because it evaporates immediately.
Oh, because it's
it does not drop. It evaporates.
Ah, okay. And then down here, just some of the other accessories. A nice wall plate. I like the look of that wall plate from some of the other brands that I've seen out there. And then that tamper-proof, and lock it into a certain.
In public areas, for example, use a tamper-proof. Schools, offices.
Right. I got a few more slides here. I better keep rolling. I think we're going to time this out just about perfectly, Thomas. And there it is with the tamper-proof.
You see it with a tamper-proof device.
Cap at the
so it's a very robust. Okay, a thief who has an Allen key can take it off, but most of them don't have an Allen key with them.
Okay.
And to be honest,
I started taking an Allen wrench kit with me now when I travel in hotel rooms, because a lot of the windows now, they lock them with an Allen wrench and a little clip in there. I like to open the window sometimes if the temperature's right, so now I keep an Allen wrench set with me.
Bob, you are one of them.
Yeah. But I wouldn't have a metric one, possibly. So. I think you talked about this wall-mounted thermostat also.
Yeah.
I think you said in Europe there's actually a box that fits in. It's the same box.
Yes, in Europe it fits on the box where we have the electrical plugs in, but it will not fit on the US boxes, I'm sure.
No, it's a different box.
But you can mount it straight on the wall.
And then just take the tube.
Yes, right.
All right, and the same looks like about the same settings on that dial there as on the valve.
Yes, it's all around, and then position 3 is, for example, room temperature.
Okay. All right, I think we just got a few more slides left here. All right, let me just try and get a couple questions for on this here. It's replaceable too, as long as no damage occurs. I think he was talking about the cap tube there. 30 feet, yeah, well, I don't think we have a 30-footer. What have we got here? Okay, so this is just showing an application.
Zoning, yeah.
With the wall-mounted versions. And then now you have to be within a distance of that, and this isn't typically very doable that you're going to have your manifold that close to where this valve could,
But you don't have to place a valve right to the manifold. You can place it somewhere in the tube on the way to the manifold, if you like.
Oh, I see. Okay.
To do zoning.
Yep. Now it said, can this wall thermostat one be set as a tamper-proof? Like, can you lock that so people can't?
You can limit and lock the temperature inside, but it's not really tamper-proof.
So they could snap off the cover. And
yes,
sit
right.
Yeah.
And to be honest, you cannot find one head on the market which is not destroyable in a school. The best is you make a fence around 2 meters high, 3 meters distance.
Well,
so all tamper-proof heads are finally destroyable.
Yeah. Over here we put those big plexiglass boxes over, and then it just kind of makes it more,
but then
a challenge for somebody to get in there. You'll see where they'll break the little things off the bottom and try and reach up in there.
But if the problem is if you cover it, it cannot feel the room temperature anymore.
Right. Yeah. So. You got to be careful what you ask for. But here's a classic example where the remote sensor that we've talked about was used on a.
So the position below the radiator is not bad because it's then placed in the convection of the radiator, so it detects the room temperature not bad. In Europe, I would say this is the most known position for the remote sensor below the radiator.
Yep, and it's out of harm's way there. So basically, what's happening is a cool air that's coming across the floor.
It's sucked in the radiator. First it goes over the sensor, then it sucks in and it's thrown out warm on the top.
Okay. Because this isn't going to be very attractive for most people having that sensor.
No, if you're married and your wife will hate this position.
Thanks. We talked about that a little bit earlier, using it for an injection mixing temperature control device there.
An injection
look at that. How's that for timing? Well, this has been great. That's been, I learned a lot when we did the practice on Monday, and I learned even more now, which is the indication of a good webinar. Any questions that I didn't get to, I'll try and get to them when you.
But I'm available the next years, so you can ask me the questions.
Okay. And this is what on the website now is our new price list is on there. And what we did this year is we combined all of them into one catalog, and it's. As you go to the website at caleffi.us, you'll see this picture of this price book on the very upper right-hand column. So you don't have to search around through the text to find a new price book. So that makes it easy for you guys to see the new product and what we've got it all in one spot, which makes it easier. We're on Twitter now, so if you want to tweet something, we can answer some questions there. I'd like to keep in touch and see how we can improve it. What else? Oh, this is something we started doing on the last webinar, and we're going to continue to do this. It seems to be working out for people. It's hard for me to go to every jurisdiction in the U.S., the cities and the counties and that, and see what they need for continuing ed credits as far as a diploma or something. So what we're going to make available to you, and we're going to email it to you, is this certificate of participation is what we'll call it. In most cases, your AHJ, your authority having jurisdiction, will accept this as proof that you did this one out webinar. One thing that I did notice that happened on this is we're going to send it to whoever's email that you sign in as. If you're signed in on somebody else's email with somebody else's name, you're going to get a certificate that might not have your name on it. So let us know that if you're trying to sign in under your own email, so we get the right name on this when we electronically send this to you. And next month, I should say, my son Mac, who spent some time working over at the factory in Italy, is going to do a little virtual tour of the factory, and I think that's going to be fun. I know he's been working on it a lot, so he's really putting a lot of time and effort into that, so please tune into that. Thanks, everybody. It's a couple minutes after. It's a big round of applause for Thomas for